Yes, recording.
All right, let's start. Are you recording?
Yes.
Okay. So yesterday we went through the rate region, how to compute the rate region for uplink, multi-user minus case, and also yesterday we decided that generating a rate region like this will be one of the homeworks for next week's Thursday. Quite straightforward implementation of the math. Then there will be also a special case where we replace this per user power constraint with some power constraint. And that has actually connection to the downlink case when we use uplink downlink duality. So we can use the same solution to compute the rate region of the downlink case after applying appropriate downlink uplink conversion. So how this downlink rate region will look like approximately. See this color. Okay. So if you're plotting the rate region for uplink first, we'll have this type of shape. Right. And this is with individual power constraints per user. The rate is rate per user is upper bounded by the single user capacity using that power. Now, if we replace this user-specific power constraint with a total power constraint, sorry. So for two user case, so we will have actually P1 plus P2. So in the one extreme, we can allocate all the power to one user. So we get basically 3 dB gain here. But the rate region will change. It will be something like, there's still the time sharing region here. Slightly different. You will see when you compute it. Okay. All righty. So, of course, as before, we can generalize two user case with any k use case for any decoding order you want to new k or priority order, which leads to a decoding order. Obviously, the rate region is more complicated to plot. Like you might recall that for the single antenna IWGN case, it looks like this already. Right? So obviously for the multi-user case, it will have similar shape. First region, there's the some rate region, but then there are some girth regions and then flat regions below. Okay, let's consider a case 3 users. Just to verify that this general formula works. So let's assume that we have 3 users and the priority order is mu1, mu2, mu3. Right? So really the user 1 is the prioritized user, so it should be decoded last. So then we can write the rate region, the weighted sum rate maximization as nu1 times R1 plus nu2 R2 plus nu3 R3. Obviously, if we now plug in, assume that this is decoded last, this is decoded first, then we will have again these complicated rate expressions, right? That are neither convex nor concave with respect to all the variables. Maybe okay, we could write this actually just for fun. So this would be log det I plus 1 over n0 h kx1 h1 permission. It's fine, this is concave. But then for the second user, user 3 is already removed, assuming that MMS is sick. User 3 is removed, but user 1 is remaining. So that will appear in the rate expression. Log I plus the interference from user 1, h1, kx1, h1 emission plus n0i inverse times h2 kx. Right? This is the rate of user 2, assuming it's decoded. Now, rate of user 3 would be straightforwardly considering both 1 and 2 as interference. h1 kx1 h1 permissions plus h2 kx2 permission plus n0i inverse h3 kx. So this would be just plugging in the expressions. But if you wonder where does this come from, again you can just plug that into the mutual information, right? Mutual information between x3 and y would be entropy of y minus differential entropy of y given x3. Then you plug in the formulas. Okay. Okay, this is of course we cannot compute this because this one here is a concave function of kx1. This term here is a concave function of kx2, but convex function of kx1. Here, concave function of kx3, but convex function of kx2 and 1. Right? So, convex expression. So what we do here, we rewrite this R2 and R3. So we write R2 to be some capacity over 1 and 2 minus the capacity of 1. Right? So after the user 3 is removed, some capacity of user 1 and 2 is given by this expression. And then removing the interference-free capacity of user 1 from the sum capacity of 1, 2, at 2. And similarly, for R3, we can write it as C1, 2, 3. This is the sum rate of user for all users minus sum rate of 1 and 2. Okay. So now you can write this, then just plugging in And write this as mu1 C1 plus mu2 C1 2 minus C1 plus 3 times C1 to 3 minus 3 from 2. And rearranging the terms, we get is mu 3 times C1 to 3 plus mu2 minus mu3 times capacity of some capacity of uses 1 and 2 plus mu1 minus mu2 times C1, right? And we know these expressions for all these terms. C1, 2, 3 simply mu3 times log that I plus sum from I from 1 to 3 is plus mu2 minus mu3 log I plus sum from 1 to 2. And finally, the single user capacity of user 1. Okay, now you can see that all the terms here, this is a concave function with respect to all the variables. Concave function, right? So this is a convex problem, provided that these constants are positive, right? But we assume here that mu1 is larger than mu2, mu2 is larger than mu3. So everything holds, right? Yeah. And this is generic, right? If k equals 3, just plug in those values and you get it, right? So obviously you have to so this formulation holds only for this priority order. If you have another priority order to cover all the other decoding orders, so other parts of the rate region, you have to change the indices here, right? Coding. Because this gets also complicated. Now, if you want to compute the rate region for 2-user case, you need to quantize. You have to get decide certain granularity. If you want for the rate region, 100 points for it. 100 points would be fine. But now, if you go to the three user case, you get, if you want to get the same granularity, that's 100 by 100, 10,000. It gets complicated. Right? If you want to generate a 3D rate region for 3 users. But anyways, going beyond 3 doesn't make sense anyways, because it's difficult to depict, right? But the same applies. Okay, rainfall extension frequency of time selective case. You just add subcarrier indices. If you assume that we have a frequency selective, you assume we have an FST that converts frequency selective channel to flat-fading subcarriers, like parallel entropy parallel channels. So you should add here subcarrier index, and also the transmit covariance matrix, also subcarrier specific. And then you add here a summation over subcarrier. That would be the sum rate over subcarrier. And that's it. And also you should add here summation here. Summation over the subcarriers is upper bounded by the power constant. Otherwise, it's working plain. Sum of frequency. All right. This I think we discussed already, but let me just remind you what it is about. So let's assume we have the base station, multiple antennas serving a single user, say downlink. This is channel H, well, HK. So then we have some interference coming from somewhere. This applies both downlink and uplink. Just so this guy, this base station is serving, for example, this user here, right? But it's interfering this user over here, right? So that interference adds up to the noise, right? So from this user perspective, the received signal, user K, if you're sending xk from here, this is the channel between the serving base station and that user K, and this is the transmitted signal vector from the serving base station. And then we add some Gaussian noise, assuming that all the signaling is Gaussian, then also it's Gaussian. But it's not necessarily any more white, right? If this link was not there, then the noise would just consist of the thermal noise introduced by the RF at the receiver, right? And that we can assume to be Gaussian distributed and uncorrelated over antennas, right? So that's why it's called white. White means uncorrelated. So the noise process in each antenna is independent, not correlated. That's why the covariance matrix becomes diagonal, right? Now, if we have some interference here, let's say the ZA could consist of whatever transmission from this base station. Let's call this HRK. So this is the part that is introduced by this interference. Or we can call this simply a vector I. is a vector I that is caused by the interference at this user K, right? But we don't know about the system has some knowledge somehow, maybe via explicit feedback. The base station knows the covariance matrix. So the user can estimate actually the covariance matrix of the noise process, right? So let's call this depth K. Okay, now it's confusing. Small z. Let's call this something else. I includes z there, consistent. Small z, okay, and capital Z. Okay, so the covariance matrix capital ZK simply expectation of over samples, like time samples of the received noise plus interference. Expectation of ZK. That's the covariance matrix. That includes all the interference plus noise. So this one, if you go inside this ZK, it's not anymore diagonal like the noise case, but you have some complex values here. It's a full matrix. Complex values. Okay, so if we have this type of model, and we want to just maximize the rate, given that this interference here is fixed, right? Given that covariance matrix of the noise plus interference is fixed, and we want to maximize the rate for this link, right? So we can now write the visual information. Visual information between xk and yk. That's the, and we maximize this mutual information. That's the capacity. Okay, we can write it as always. Differential entropy of yk minus differential entropy of yk given xk, and then plug and play. Now, covariance of yk includes this interference plus noise component. So differential entropy of yk given as locked ie hk kxk hk permission plus z capital Z. Covariance of y. When you take the covariance of this, of course the cross surfaces appear, then you have the sum of individual covariance. Okay? And that's it. And then when you remove xk from yk, what is left is plotted by e capital Z. Okay. There. So this is the rate expression. You can see right here. Okay. Of course, we can take the ZK inside. And this can be this can be written equivalently as plot det I plus det inverse A HK KXK square root inverse. These two are equivalent. We have done this several times. Sum of lots is lot of products. Product of determinants is determinant of products. And then using the det I plus AB equals det I plus BA, you get to this. Okay. And now we can call this term as HK tilde because Z is fixed, right? HK is fixed. So we can just equivalently call this. We can just combine these two matrices into one and call it H tilde K, H tilde K, right? So now we are back to the point-to-point MIMO with widened noise. Okay, you can directly, if there are different ways to invert the matrix. You can take eigen decomposition of matrix. It's an eigenvector. And then simply the Z inverse, square root inverse correspond to the square root inverse of the diagonal terms times the eigenvectors, the Hermitian eigenvector matrix, right? So the inverse operation becomes very simple after you do the eigen decomposition, because then you just invert the diagonal eigenvalue. All right, but anyways, it's equivalent to just plugging, writing in MATLAB. Well, you can write in MATLAB directly ZK. It might do that actually we have the eigen decomposition. I'm not quite sure.
Or you can SQRTM, square root of a matrix.
Yeah.
QRTM.
QRTM.
Square root of a matrix.
Yeah. And then anyway. Okay. Now when you plug that in here, you get the the point-to-point MIMO expression. Right? And then we have the solution. SVD of this, the KX, the optimum KX has structure as we said last time. KXK. We can split that into V, T, V Hermitian, where the V is the right singular vector of this widened matrix. Okay, and this P is found by water filling over this singular vectors, singular values of widened matrix H2. Okay, so quite straightforward. Okay, there's a special case. You used to have actually an extension of this as a project work for wireless communication. The old version of wireless communication to implement iterative water filling to compute the sun rate. Sun rate for the multi-domain. Sun rate meaning that now we are interested in time sharing region. All the users are equally important. Sum rate with all the same sum rate can be achieved with all decoding orders, but obviously the rate per user depends on the decoding order. Sum rate is the same. Okay. So obviously, when you plot this scenario in here, all the mu's are equal, right? So you have some mu here, but all these other terms disappear, right? And 0. So what we have left is just the sum rate expression. Okay. As it should. So, of course, this is a convex problem, and we can just plug it in solver and get a optimal transit coordinates matrices with K. But we can also get an iterative version. You can actually see that this has a nice structure. We have a concave objective function, and then all the constraints are separate, right? All these transmit power constraints or covariance. Well, transmit power constraints are constrained by individual user-specific power constraints. Okay. So this actually a hint that this is a coordinate ascent, block coordinate ascent, or there is a block coordinate ascent algorithm where you can solve all these variables one at a time by keeping the others fixed. And this is exactly what will follow. Well, first some optimization theory. Speculate about the optimality of the solution. So we can write the dual the Lagrangian for this problem the standard way. It's the Lagrangian. We have the objective, and then we have relaxed the constraint to the Lagrangian function by assigning these dual variables. Right? So for the positive semi-definite constraints, we have the dual variable also ESD. Right? For the scalar constraints, we have just the scalar lambda k. So then we have the then we can look at the well before we go there, we can rewrite the sum rate expression. Right. The received signal, let's say from now we have the uplink. I'll use the uplink case. The 1, 3, all of these are communicating with the base station H1 3, the received signal H1 H1. Well, in general, the summation over all the users K plus noise. So we can obviously write this from a user K perspective, right? So we can separate user K plus all the other users. But from user K perspective, these contributions are seen as interference, right? Z. Okay. Right. So we have the same model as earlier. Right. If this is fixed, then we have the same point-to-point MIMO with interference. You can see this, it's equivalent model to the one that we discussed earlier. Similarly, the sum rate expression, we can write in terms of user K, the HK, KX, K, HK remission plus summation. KXI. So this is the interference term with respect to user K. Of course, we have the noise here as well, included in the formula. Or it can be, the noise can be included also here and then also outside, right? Locked in control. Anyway, that's maybe confusing. So of course this is equivalent to that one. But if this is fixed, let's say ZK, then we are back to point-to-point optimizers, right? With fixed interference. So now when you compute the Lagrange, the differentiate, this is one of the KKT conditions that the Lagrangian should vanish. Lagrangian with respect to the primal variable, which is the KXK, should vanish at optimal solution. So when you compute the Lagrangian, differentiate the Lagrangian function with respect to matrix KXK, you get this expression. Right? So then we have this additional constraints for the KKT or conditions. We have the complementary slackness that the product of the covariance matrix and the corresponding dual variable. This is related to the positive semi-definiteness, so meaning that ours should be non-negative. This product should be 0, meaning that, and then we have this primal constraint, KXK, equals PK. Anyway, I have a mistake there. There's a mistake. Inequality here. If we had an equality here, then we would not have complementary. Complementary slackness is only for the inequality constraint. So what it means that either the covariance matrix is positive, strictly positive, or the dual variable is positive. And here we know that from the optimal solution that assigning any power smaller than pk strictly decreases. So we know that at the optimal solution there should be equality. So we can also claim that one variable has to be 0. This goes to 0. Okay. When this goes to 0, we have a diagonal here. This term becomes diagonal. So what we can see from here that the KKT conditions are equal. The single user minimum with colored noise, assuming this is the ZK. When you compute the KKT solutions for the single user minimum with fixed ZK, you get exactly the same formula. So at the optimal solution, all users, of course, all these of each user K is equal. So basically, at the optimal solution, assuming all the other transmit covariance metrics are fixed, the optimal solution is to just do single user water filling, given the other user covariance metrics are fixed. Okay, so it's easy to show. It's actually, the more details you can find it in the paper. But when you start doing the block coordinate ascent update of this, basically start from somewhere and assume all other transmit covariance metrics as fixed. At each step, you're guaranteed to increase the objective, right? So this suggests this practical solution, what we call iterative water filling. And we start optimizing these transmit covariance matrices for each user one by one. Right? So you can start from initial assumption that all transmit covariance matrices are 0. Okay, then you go to this iterative algorithm. K goes from 1 to k. And since we have assumed in the beginning that you can initialize this with whatever values, it still works, but you can very well start with the 0. It could be a random matrix, random ESD matrix that meets the power constraint that is feasible, still guaranteed to converge monotonically. But this is actually something that is nice to illustrate what happens. Like when we assume that all the transmit covariance matrices are 0, for the first user that we optimize, the interference is 0, as if the interference is not there, right? So there's only noise. So the first user to be optimized is single user minor, right? As if the other users were not there. Now when we go to the second user, the KX1 is already optimized, but the KX1 adds up to this interference plus noise. Okay. And that ZK is now incorporated into the single user minor with colored noise optimization. So basically, just whitening HK with ZK inverse. You can KX1, KX2, and then you move on. If you have two users, you basically just switch between these, optimizing these two users. Right? It's very simple. You don't have to solve the case as a you don't have to use CDX. Just reusing your water filling that you have already implemented for the point-to-point minor case. So since this is a coordinate ascent, it's guaranteed to converge. So whenever we update, when we do the it's like that. You can think the surface as like a bowl or like a concave, like a hill. So you are just approaching the hilltop from one direction, right? So you just move this direction, and then I don't know how to. So you just approach this hilltop from K directions. You just optimize one dimension at a time, right? Okay, so we can see actually what happens for two user case. The first step, right? Assume no interference from user 2. So this is a point-to-point minor. So this is the absolute maximum that can be achieved by user 1. And so it goes to this one. And now, this is actually something that we already discussed yesterday. Given the interference from user 1, we can get the grade of user 2. We don't have that expression anymore. Not bed I plus kx1 h1 right. So this is the interference from user 1 plus noise. So when we optimize the kx2 given fixed interference, right, using the widening process, that is right here. This is the rate pair when we give that we should use or you should use when you compute these two extreme points for rate region, right? Giving absolute priority for user 1. Okay. You can also have the other way around. You start from user 2. You just change the index order in the iterating water filling. You will start from different dimensions. Okay. Now, given the fixed kx1 and kx2, you can switch the decoding order, right? Now the kx1 is optimized for the user 1 to be decoded last, and kx2 is optimized for user 2 being decoded first. But you can use the same covariance matrices and just switch the decoding order, right? So the user 1 rate would be then just changing the indices. The user 1 would be now interfered by user 2, but with this suboptimal covariance matrix. So this point here, this would be the point given the first optimized kx1 and kx2, but just reversing the decoding order. So now from that, we can now switch the decoding order and then optimize kx2 given kx1 fixed. Right? It's just that we have two users here. Start from both are 0, optimize kx1, single user, that gets you the point, the first point there. Then that kx would go, when you go to the 2, that 2 would contain the interference from user 1, and then you get kx2. Now you go back to user 1, and you have the interference from user 2. Right? So when you optimize your transient covariance matrix, given the interference from user 2. And that's exactly what happens here. You move from this point to this point. Okay? Then you switch the decoding order to this point. You optimize the transient covariance matrix of user 2 given the re-optimized kx1 and so forth, right? So you just move gradually until you reach the sum rate region. Yeah, makes sense? It's actually something we could include in the just to illustrate this. It's a nice exercise. It's just a little extension of the weighted sum rate. What do you think?
Yeah.
What do you think? By the way, let's take a break now. And 7-minute break. How was the first exercise? Okay, just a final reminder. I'll give some MIMO system implications. So in general, the multi-user minor, obviously the degree of freedom limits per user apply. So for each user, the number of streams, let's say number of streams that are not interference limited, right? We can have more streams in principle. You can assign, if you have, for example, more antennas, more transmit antennas and receive antennas, you can assign more streams, but then those streams that are, let's say, above the spatial degrees of freedom will have very small rate because they are interference limited. So in practice, when you compute the solutions in a multi-user setup, when you look at the transmit rank of the transmit coherence matrix, the user is applied, right? So even if the MTK would be larger than NR, the optimal solution would not allocate more streams than the receive one. And then we have the sum degrees of freedom across all users. So this is when you optimize, right? So of course, when we have the case when the CSI is not available, the optimal solution is to assign one stream per antenna and then assign equal power. Right? Then obviously you are transmitting more streams, but then the rate per stream can be very low for the ones that exceed degrees of freedom. But then when you optimize KH, when you have the CSI, local CSI, typically this DOF limits hold. And these are obviously for the linear schemes, these are the absolute requirements, right? Very close in R. Second bullet. Number of users on that. Okay. If you have as many users as receive antennas, then having multiple transmit antennas, typically, because in uplink, every user, if you optimize the transmit covariance matrices for a single channel realization, and then you have the power constraint per user, you are kind of forced by the optimization to assign at least one stream per user, right? So when you have as many users, they have 4 antennas here and 4 users, but each user has multiple antennas. Then, because you have individual power constraints per user, because of this power constraint, if you don't assign any streams to this user, but assign 2 streams to that user, we would not use this power at all, right? And that would be bad from the utility, the sum rate objective perspective. You would be not using all the power, right? You would be using all the, you could assign, for example, 1 stream to this guy, 1 stream to this guy, 2 streams to this guy, and 0 to this guy, right? But then you would be not using that power at all, right? So in this case, the solution will for sure, it will have a solution where you assign only 1 stream. So these multiple antennas here, they provide additional beamforming gain, right? It just boosts the SINR per stream at the receiver. You can focus your transmitted power towards the base station, given the interference from all the others. Okay. And if we have more users, if we have let's say 5 users, but 4 streams, still we would assign most likely 1 stream per user. But when we decide the decoding order, if we decode this first, assuming all these other interference, we have only 4 degrees of freedom to remove the interference in the space domain. So this guy would have very low rate, less than 1 bit. Because it's interference limit. We cannot remove the interference from these 4 other streams by spatial process. So in this case, let's say a simple solution where you split the users into groups. But if you can use the same power later, it would be almost optimal. Okay. If you have final frequency selective fading, so let's say OFDM, then you have more degrees of freedom how to allocate the power across both space and frequency. So in this scenario, especially in the low SNR, it might be that some users are not served at all in some subcarriers, right? In the extreme case, there's only 1 user which is active in 1 subcarrier, because you can use that power budget more efficiently in some other subcarriers. You could, in the extreme case, each user would be transmitting in 1 subcarrier only, right? Yeah, if you think about the water filling, that's what would happen. But the solution would be orthogonal. One practical challenge, if you want to implement this in practice, let's say this iterative water filling, assuming TDD, downlink is actually more difficult than downlink. Because downlink is easier because base station has all the knowledge, right? But if you assume that we have a TDD setup, so each user could estimate its own channel from downlink pilots, right? But this user would not be able to estimate the other user channels, right? There's no idea, just from the TDD type signaling. So these channels should be explicitly fed back. That would be, of course, huge overhead. Or if you think about the water filling algorithm, when we optimize the transmit covariance, if we assume that this transmit covariance matrix optimizes and happens at the user, right? So the user has knowledge of HK from the pilot, downlink pilots, but no information about the ZK, because that ZK is the interference covariance matrix measured at the base station, right? So if we wanted to compute KX, optimal KX, at the user side, we should have this knowledge at each user, right? So we should report ZK. If we optimize now KX1 here, we should assume these are fixed and then report back to ZK, optimize, and similarly. And that's, of course, something that cannot be implemented because you should iterate to exchange a lot of information. It doesn't work in practice, right? What you can do is that the base station has all the knowledge of HK. You can compute this at once, iteratively, or using CVX whatsoever, and then report the optimal KX to its user. Of course, that takes some signaling effort, right? Or not, maybe not the transmit coherence methods, but actually just decompose it and send the beamformers. Or it could assume certain code book. It just decompose KX and then finds an index in the code book which is closest, and then just feeds back the index that, okay, use this recorder from this code book with this index. Okay, but then of course it's not exactly optimal because there's some rounding, right? Because you would need infinite code book to cover all the possible solutions. So, not very practical, but you can get actually pretty good performance if you ignore the interference, because the base station can still do the MMS is sick, right? Even though the transmit coherence matrices are not exactly optimized for the interference, optimizing the KX just for the local CSI, just ignoring ZK. Let's assume that it's M0I here, and each user just optimize KX, assuming no interference. That works quite well. And it works even better if you, and it's more practical, if the base station informs that, okay, this is the number of streams that you can transmit, right? So the base station would then, each user would then limit the rank of KX based on that rank command coming from the base station. Right? Naturally, so for example, in this case, if we had, let's say, 4 users, okay, and relatively high SNR, so all 4 users, if they ignore the interference, they would send 2 streams, right? If they are not constrained by anything, they would assume no interference. There's 2 degrees of freedom, high SNR, assign 2 streams. So in total, there would be 8 streams and just 4 antennas. That's inefficient. It still works, but this extra streams will have very low rates, right? The simple strategy would be that, okay, base station knows that, okay, I'm serving these 4 users. Okay, assign 1 stream each, right? So then it's easy for each user. Just take an SVD, pick the strongest single vector, and assign all the power to that single beam. That works very well in practice. Okay, let's move on to downlink. Any questions at this point? Okay. I recommend to read the book. The book is really self-explanatory. I have learned this stuff just by reading that book by myself. So it should be doable. So please read those subsections beforehand, before the next week lectures, and also the appendix. You can have also look at some of these journal articles beforehand if you have time. So in this slide, we will cover we will start introducing this uplink downlink duality, and we will constrain us first to the linear downlink. So assuming that the number of streams does not exceed the degrees of freedom, and no successive interference cancel. Just starting with the degrees of freedom analysis in the downlink duality, showing that the sum power for a set of SIR constraints that are assigned in the downlink and minimizing the power, or finding a power allocation to meet this downlink SINS holds also for uplink. If we switch the role in transmit and receiver, the sum power is the same or same as. This is the key result that we will then use later on to convert the difficult downlink optimization problem to solvable uplink problem. We will look at this PCM beamforming very briefly here, because then in the next slides at L5, which is almost complete now, we will delegate much more. Well, we will delegate that entirely to downlink beamforming for all kind of different with different assumptions and objectives and CSI uncertainties and all kind of details. All right, then after this introducing the uplink downlink duality, then we will move on to this nonlinear downlink. We will discuss about this dirty paper coding idea, which is kind of equivalent to MMSC SIG in uplink, but instead of subtracting, let's say, subtracting something which is something at the receiver, we pre-subtract or pre-compensate at the transmit. This is the transmit at the base station. And then we will start with the simple single antenna case, introduce the basic idea of the dirty paper coding, then move on to the multi-antenna downlink pre-coding using the idea of dirty paper coding. Then uplink downlink duality for the nonlinear. It's a relatively straightforward extension of the linear case. And then finally come up with the downlink sum rate and rate region beyond this dual uplink formulas. And then extend it to the multiple antennas. Okay, so we have covered this the impact of multiple antennas, both uplink, multi-access channel, and downlink broadcast channel. The benefits in general is lower diversity in beamforming gain, spatial multiplexing gain, even for the single user case. And for the multi-user case, we can use these multiple antennas to provide simultaneously multiple data streams from or to multiple users. So unlike in uplink, where we cancel the interference at the receiver, in downlink, we cancel the inter-user interference or pre-cancel at the transmit based on the global CSI. Okay, the multi-user MIMO stuff we will discuss in slides 6 later on. Okay, let's start with the downlink system model. So in this slide, we have some time invariant channel. The channel is fixed. So that's for simplicity. Of course, everything extends, and we add here also index that the channel keeps changing. We do the optimization over time as well, but it gets hugely complicated, and you never do that in fact. You don't know the channel in advance. Well, you know the statistics, and you do something. If you have a water filling type solution. But here we just for simplicity assume a fixed channel realization. So we assume that there's we want to design decoders or beamformers for a certain transmit interval where the channel is more or less constant, right? So meaning that in a TDD case, you can estimate that the fading is slow enough that when you estimate the channel from the uplink pilots, and then design these decoders based on these uplink estimates, and we assume that the channel stays more or less constant. Well, here we assume that it's exactly constant. Then we apply this designed decoders for the downlink transmit. Okay, receipt signal model. So we start with the single antenna case. YK. So the receipt signal consists of transmitted signal vector X from all antennas, propagated over a channel vector HK. So this inner product between these two vectors gives us a scalar of the desired scalar of the signal component that now includes contributions to multiple users in parallel. And then we add the Gaussian noise at the receiver. So now we can start going a bit deeper into this model. Now we have the downlink model, single antenna. So the transmitted signal vector is a superposition. Now we superimpose all transmissions or all data streams to K users on top of each other. And now this separation happens via these precoders that we assign for each user. Right, so we assign a precoder. This is the normalized precoder. We call it vector, and then we assign a power. We call it. We have some power constraint transmitter, and then we have a symbol for each user. Decay. Right. And now when you plug that X into the system model, you can pick. If you look at from user K perspective, now you can pick from the transmitted signal vector X your desired component. This is the desired component, and these are the interference components. Right? Just simply plugging that X vector in here and separating the desired component from the non-desired component, you get the equivalent system model. Right? So here you can see that the impact of interference. Right? So this is the desired, this is scalar, this is that we want to maximize for given user, and these terms we want to minimize in general, right? Depending on the objective. How much we want to. Of course, sometimes you want to even push this almost to zero, right? This disappears. This happens in the highest level. This is what we will see. Because in general, we want to push this component here to more or less to the same level as the noise, right? It does not make sense to push this component much below the noise level, because the noise starts to dominate anyways, right? On the other hand, if this is too high with respect to noise, there's something you can do better, right? So similar to MMSC in the uplink, that you want to find precoders that simultaneously maximize this term, but push this interference term to more or less to the same level with the noise. Okay. If you do zero forcing, you don't care about the noise, you force this to be zero. Right? And that's not a good solution in general, right? Because then it becomes, then when you force something to be zero, then this U is optimized just to make this cross product to zero. And then you don't have the match filter. You don't have the beamformer is not necessarily matched to the desired component, right? We have this discussion about the interference subspace, and this is the orthogonal complement to it.
And then we have the say that the channel, the desired component. Let's say this is the okay, this is actually a bit complicated here because we from the single user perspective here we don't see the other user channels, but of course the other user channels should be taken into account in computing the precoders. Let's get back to that later when we solve self-forming. Okay. All right, so you can also write this compactly. You could just stack all these received signal. Let's say you could generate a vector y, which is y1 to yk, which is then simply H Hermitian matrix. Just stack all the vectors into matrix. And x plus n. So a MIMO model again. But MIMO with no collaboration between receive antennas. Right? But still the signal model is the same. Now you can also plug in this x here. Actually, you can also simplify this expression by collecting all these u vectors into a matrix U, right? U is just U1, UK, right? Times a diagonal power loading matrix times vector D. Besides, right? This is pretty clear by now. So you can plug that in here, HU squared plus the matrix form. So why we use this H Hermitian here is just to use the same channel as in the channel in uplink was just H, where one column corresponds to one user. Now we just take a Hermitian of that matrix. Now one row of this Hermitian matrix corresponds to one user in downlink. Okay. All right. Degrees of freedom in downlink. So let's assume some special cases first. We have 4 antennas, and then we have 4 users. Okay. So this H is a 4x4 matrix. Right. If we connect all these antennas with cables, then we have equivalent single user with 4 antennas, right? So it's a single user number. We could simply apply SVD, right? And the receiver would be just U. Again, just take the SVD of the Hermitian matrix. Apply this as a precoders, U as a receiver, and get the diagonal. You get this 4 parameters. You can do both transmit decoding and receive decoding. So transmit beamforming and receive beamforming. And clearly in this case, the degrees of freedom are minimum of NR and K. Okay. If we have more users, let's say K larger than NR, still it would be transmitting only 4 streams in this case. Right? So that's one special case, allowing coordination between receiver antennas. The other special case is now we have to assign, we have to set this extra constraint that number of users should not exceed the number of transmit containers for this to hold. For this fully cooperative case, we don't have such constraint. We know everything. We can limit the number of streams to transmit. Or if we have more users, then we have to select the set of subset of users, subset of NR out of K users, and then it holds. Okay. Okay, let's assume that now somehow by chance, and the probability of the chance goes to 0, or it's 0, that we have a situation where this inner product between any pair of I and K is 0. It is for all I not equal to K. Meaning that all the columns of this channel matrix are orthogonal, right? Then simply the match filter. You can assign the precoder to be match filter or maximum ratio transmission, right? So if we plug in YK equals HK permission UK UK I not equal to K, 8K UI. Now if we apply this beamformer, UK is normalized match filter. And plug it in here, and here, all these terms go to 0, right? Because they happen to be orthogonal. And then the system model simplifies to like single, multiple input, single output channel, as if the other users were not there, with the corresponding SNR. Okay. Another special case is the zero forcing. Again, applies to K smaller or equal to MT scenario. There we apply, there we compute the or assign the precoder UK to be normalized columns of the pseudo inverse of channel H. Okay, this is the zero forcing solution. So let's see what happens when we plug that in here. So just to see it easier, how to solve this. Let's consider the vectorized form. The HU now it's U vector is assigned to be the new matrix is inverse, and then normalized. So we have to normalize each column. You can write this as the matrix. Okay, we can write it. It's a bit complicated, but this is the normalization, right? We divide it. Basically, this is the same as normalizing every column of this matrix with these values. Okay. This is equivalent. It's just bringing this. We have this normalization, the vector, right? So this is equivalent as multiplying this matrix with a diagonal matrix of Decay inverse, just like that. We can do the math too. You can play with the math if you don't see it directly. But this is equivalent. It's equivalent to, let's say, doing this individually. Where Zk is. Oh, just like there. Okay. Now, if we plug in this expression over here, you can see that we have H Hermitian, H times H Hermitian, H inverse. And we have this diagonal power loading matrix here. So we can actually plug this one inside. So we get a diagonal power loading with E1 square root divided by Z1 norm. Just multiplying, we have a diagonal P matrix with diagonal Z inverse matrix. Times D vector. Okay. You can see that this is an identity matrix. So by doing this operation, no interference at the receiver. The signal model becomes diagonal, right? So D1 does not interfere D2 and so forth. So we can equivalently write this as, let's say, 5K equals PK square root PK divided by Zk plus noise. Yeah, same as here. Okay, just follows from here. This time D1 okay. Okay. If we D1 from here, this times this, Y1 would be equivalent to this here, the first vector, rho times vector of this, and here, because these are 0, it's only the desired data. And then the corresponding, that's why you get that equivalent channel. So SNR, signal power over noise power, and you get this SINR, which is the same as in the uplink, right? When we looked at the zero forcing. But at least in the point-to-point model, we discussed about the zero forcing, and it's exactly the same expression, right? So all these special cases have at least it's a bit more less restrictive because we can do it. Well, it can handle larger case. The first case can also larger directly handle larger case, larger than MT. But for these two other cases, at least we have to choose a subset of users which is smaller or equal to number of transmitters. Right. If we try to serve, let's say, 5 users with 4 antennas, zero forcing would not be possible. Right? You can see that this would be 5 by 5 matrix, but rank 4. Right? So there's 1, 0 eigenvalue of this matrix, and inverse of 0 would be infinity. So it's an output of 0. So all the strings, if you try to do zero forcing for 5 users with 4 antennas, all the SIs would be 0. Okay. All right, let's move on. I will just basically introduce the SINR. Right? So we noticed that if you are interested in the signal to interference noise ratio of user K, we have the S, the signal part, the interference part, and the noise part. Right? So the SINR is simply the SINR for user K is expectation. It's a variance of the signal SK complex conjugate divided by expectation of the interference plus noise complex conjugate. Right? So now you just plug in SK, that would be HK permission UK DK, then DK complex conjugate UK permission and HK. Right? SK and UK are fixed for a fixed channel. The expectation goes inside, and we know that expectation of DK complex conjugate is 1. This is the normalized transmitted data symbol. So this is equivalent to, okay, we have DK missing here. DK goes here. So we have PK times HK permission UK square. Okay. And then similarly for the expectation, we get all these terms, the I terms and N, and then interference and noise, they are independent. So the cross terms vanish when you take the expectation. So then you have just the variance of I plus the variance of noise. Right? The variance of I is simply so you can expectation of I and expectation of separately, right? Because they are independent. And then we have HK UI plus NY. Right, so that's the essence, SINR. So this is in downlink, it's different than in uplink. In uplink, recall that these indices are reversed. In uplink, we have 4 users accessing over different channels the base station, right? And each user is received with a user-specific receive vector, UK. Right? So the uplink SINR would be same as here, but reversing INK. See this? In the downlink, because we are sending a superposition, we are broadcasting. We're broadcasting signal, the signal X. And this broadcast signal is received at each user over the same channel HK. Right? So the interference comes from these other recorders that are simultaneously broadcasted to other users. Okay? This is the difference. This is the difference that we will use in the uplink downlink flow a lot. Otherwise, it's the same. If these beamformers are normalized. Okay, let's quit for this today, and then next Tuesday and Wednesday I intend to cover most of the slide set 4. So it's somewhat intensive, so please study as much as you can in advance. All right, see you on Tuesday, and tomorrow there's the exercises.